see how it works. You should be able to access the YouTube link from here at work. If not, let me know and we'll work something out. Has anyone looked at YouTube videos at work? No. Yeah, I guess you're okay. You wouldn't want to admit that. Yeah, let me know if there's any quality problems with the video or the audio. In regard to the slides itself, the goal is not that you be able to read the slides through the video, but you'll have the link to the slides so you can follow along at least. If you miss a class, you're not completely out in the cold. Sound good?
Yeah.
Anyone have any issues about being recorded? Okay, if you do, well, I asked last week and no one said no, so. Yeah. And if you've ever been curious about every single strange mannerism you have, try recording yourself and talking for 5 hours. I teach a black belt course on Saturday mornings, and it's literally 8 a.m. to 1 p.m. of me standing up there singing and dancing. You think I'm entertaining for an hour? Try listening to me for 5. Yes. Any questions for me? Comments, concerns, quandaries? Other keywords, qualms? Everyone here has turned in their exam? You gave it to me. I didn't grade it yet. I have your form. Everyone else at that table has given me your exam? Cool. Has anyone gone to look back through it recently? Okay. You might want to start that because remember that the exam is creeping up. It's kind of scary to think about it, but it's less than 5 months away. First weekend in June. So we've got time, but there's not as much as you think. Anyone do anything fun or interesting? Nothing fun? Nothing interesting? Hey, where's our friend that always does fun and interesting things with his kids?
Yeah, I don't know.
Oh, adjustments occurred in processing, so he's pretty much processing.
Okay, so hopefully we can get him back watching the videos. So, and then he can email me and say the fun and interesting things, so I can make sure that someone in the class does something fun and interesting. Since I never get to do anything fun and interesting, I do fun and interesting stuff. In terms of scheduling, we might need to reschedule the class 2 weeks from now. I need to be in New Orleans, and I'm trying to figure out if I can get a flight that will not mess up this class. So I can go participate in a baseball negotiation. Yay. Don't ever go to law school. Nothing fun, nothing interesting? Nothing? Okay, so where should we start? So last week we did a review of sort of the roadmap that we've traveled. So we went through the idea of DMAIC, define, measure, analyze, improve, control. We went back through the aspects of DMAIC we've covered. So basically the define and the measure. So in the define, the brainstorming tools, right, the project charter, the process mapping, all that good stuff that we spent the first couple months talking about. And remembering that the output of the define phase is your project charter, where that's the agreement between the project team and the champion. And we remember how we discussed how the different roles in the Six Sigma structure, like the champion, the master black belt, process owner, etc., the green belts. So went through that. You should be familiar with those terms. You can expect to see probably about 3 questions on the exam that are related to who does what. And those should be pretty simple questions. As I related that back to the baseball analogy, if that works for you, go with it. If something else works for you, go with it. If not, just know where to find it in the slides. As you probably saw on the midterm, if you put the time in and look in the book, you'll find the answers. Particularly when we went over it, I saw a couple of you had that sort of aha moment of, that's where it was hiding in the book. So you just have to make it so that on June 7th, I think it is. Anyone know the date? 6th. Yeah, it's the first Saturday in June, so it moves around a little bit. So on June 6th, you know where to find it. Again, the exam itself is open book, open notes, so take advantage of your resources. There's nothing worse than having the answer sitting there next to you and not finding it. That being said, so we talked about that. So we finished the define phase, now we've transitioned over into the measure phase. And in the measure phase, we start to talk about statistics. And in the measure phase, we really put an emphasis on descriptive statistics, remembering that there's 2 different types of statistics. There's descriptive statistics that describe reality, and then there's inferential statistics that use a sample of data, the data that you have collected, to draw conclusions and make predictions about data you haven't collected. So in descriptive statistics, it basically comes down to applying mathematical techniques to describing what you did. So in descriptive statistics, there's generally 2 things you evaluate. One is the measures of central tendency. So the measures of central tendency basically try to answer the question of, if I were to grab a random individual, what am I likely to see? So the measures of central tendency that we talked about are what? Anyone can name them? I'll start with M, which makes it kind of easy.
Yeah. Mean.
Mean.
Yeah.
The mean? Okay, what's the mean? What does mean mean?
Average.
Average, right? So I take all the observations and I divide by the number of observations. So in what type of our measurement scales, remember we talked about the measurement scales being nominal, ordinal, interval, and ratio. Which one of the measurement scales do we generally use the mean with?
No.
Okay, nominal. Well, would you be kind to spin the camera? Actually, I can find there.
Okay.
We'll make everyone nauseous with watching the video. Okay, so an example of nominal measurements are things that have no numerical sense. So they're attributes. Okay. Did you make breakfast this morning? Okay. Did you make breakfast this morning?
No.
No.
It's not fun. Okay, I'll try something. Who does laundry in your house? You do your laundry?
Yes.
You guys are killing me. I need something that has a gender disparity.
Let's go with lipstick.
Or coffee or tea. Something like that.
Okay, coffee or tea? Coffee. Coffee?
Coffee. Tea.
Coffee.
Come on, you guys, you're killing me.
Okay.
Okay, we'll just create
Lipstick will work. See,
Let's
you.
just create the data, so I don't have to do that. So I make the y-axis count and the x-axis gender. So we see that gender is nominal, right? There's no numerical significance to men, women. You can't. So if you want to predict who drinks more coffee or tea, in this case, what would you do? Just intuitively. You would go with the one that appears most frequently, which would be the what?
Coffee.
Well, okay. Well, no, we have men and women. This is coffee preference. Coffee or tea? Coffee. Okay, so these are the y-axis represents the number of individuals who prefer coffee over tea. So we see that we have more women that prefer coffee over tea. Right? Cool. So we have our measures of central tendency. So we have the mean, median, and the mode. Okay. So this is a case of nominal data, right? It's nominal because men and women, no numerical significance. Okay. So if we want to give a good measure of central tendency, a good prediction of what we would do if we just pluck a random person and look at their gender. Which would be you? I don't know. Go on to answer the question of who prefers coffee over tea. We'd use the one that appears most frequently, right? Which would be women. And which one of our measures of central tendency corresponds to the one that appears the most frequently? The mode. That's the definition of the mode. The mode is the number that appears most frequently. So you use the mode in the case where you have nominal data. So when you can't take a numeric average. So how could you take a numeric average between men and women?
You can.
You can. So you can make an off-color joke, but we're on tape. Okay. So in the case of, in what case would we use the median? The mean. What type of data? So we have 4 different types of data. We have nominal, ordinal, ratio, and interval. Right? Hopefully this is cool. So nominal, put things in order. Nominal, group things together. So things that do not have numerical meaning. Ordinal, you put things into order. So it could be the first part off the line, it could be the last part off the line. It could be the Likert scales. So there's little online surveys I strongly agree, I somewhat agree, neutral. somewhat disagree, very strongly disagree. Those are examples of ordinal measurements. So you only know the relationship between the other options. Then ratio. We've talked about that a lot. So ratio is an example of a measurement system where there's a rational zero. So at 0 of that property, you have an absence. So if we go a little north of here, we can probably find somewhere that is 0 degrees Fahrenheit right now, right? Does that mean there's no temperature? It just means it's cold. So that would be an example of interval measurements. But you can think of if I have 0 grams of something, do I have anything? No. That's an example of ratio. So, okay. So, the mean, which one of our types of measures would we use the mean with? Yes. Why would we do that? So let's do an example. So I measure the property of lengths of sandwiches, which we will get to at some point or another, for sub-foot long sandwiches. And we find that the average is 12 inches. Okay, first off, is inches an example of a ratio measurement? If I have 0 inches of something, is there any line? No. Okay, cool. So ratio, good example. So we're going to find that we will find some sandwiches that are down here at 11, and we'll actually, depending on what subway we go to, we'll find some at 13. And we'll find some in the middle. And we'll collect some data, and hopefully we'll find something that looks like that. Right. Hopefully it will more or less look normal. But who knows? The cool thing about collecting data is you don't know what it's going to show you until you get the data. Okay. So why does the mean make sense in this case? Well, if you wanted to predict where the center of your curve is, what's the most likely value you're going to see, well, it makes sense that you take all your observations and divide by the number of observations and plot it back. Cool. Everyone cool with that? Okay. So we see that we use the mean for, in the case of ratio. What about interval? Well, let's stay with it. So let's say it's the temperature in this building right now, right? So probably the temperature is somewhere around 64 degrees Fahrenheit. Right? You probably can find some places, particularly by Beth, that are like 60 degrees Fahrenheit. And probably somewhere in the core it's like 75 degrees. Right? Everyone, and as we said, Fahrenheit is an example of interval measurements because at 0 degrees Fahrenheit, you still have temperature. It's just cold. So would this be any different than ratios? Would the mean be a very good explanation for it? Yeah. Okay, so let's look at another example of. Okay, so ordinal. What do you think would be the best for ordinal? So strongly. D-degree.
Mode.
I'd say strongly. Strong. Somewhat. Neutral. Somewhat. Strong. Standard 5 like scale, right? We filled in lots of these bubbles with those stupid online surveys. Raise your hand if you filled out one of these stupid little surveys. Yes. Okay, cool. We got everyone. I always make these assumptions, and then someone has never taken the survey or has never been to Starbucks, and I'm completely done in. Okay, so I collect this data. I find that 3 people strong, 6 people bad, 2 people neutral, 6, 2. Right? There's just the number of people in my poll that responded. 3, 9, 11, 17, 19. Ooh, nice number. So we have 19 respondents. So if I wanted to predict the average response of a respondent, if I wanted to describe what the average response for a respondent to my lovely Likert survey is, what should I report? What do you think?
The highest percentage to the answer?
So Medtronics pass around surveys like this occasionally, right? So let's make it 20. Just make it nice and easy. Make it symmetric. Okay, so we have 20. So if we took the average, what would we get? Oh, we'd be over here, right? We'd be neutral. And are there a lot of people that are neutral?
No.
No. That'd be a good thing to report. Okay, so you can report the mode that would be somewhat and somewhat. And somewhat has a T. So if there was one of these that was appeared a lot more frequently, you probably would want to report on the mode, right? So the mode's a good answer for a ordinal. But we see that in this case, it's kind of like, well, it doesn't tell us the entire story. The ordinal measurements are generally a hard one, particularly when they're the order that something comes off a production line. Because what's going to be the middle is going to be the middle all the time. It's not telling you anything, it's just the middle guy that came off the line. So ordinal is generally a hard one. There's no clear, obvious answer as to what you should use for your measure of central tendency. It depends on what you're collecting your data on. Sorry, a bit of a trick question. How do you thinking? It's nice and early. Okay, and nominal we saw was the mode. Cool. Okay, so when do you use the median? Right, the median is just the middle number. So we gave a couple examples on when you use the mode. We gave some examples when you use the median. I'm sorry, the mode, the mean. We didn't do an example where we use the median. So why should you use the median? Well, ratio and interval are pretty much for our purposes, there's another technical difference, but for our purposes, the difference between interval and ratio is that one has irrationals here. So the space between the intervals is the same, and if you want to approximate where the center of it is, probably a good bet to go with the mean. Cool. Any ideas on when you should use the median? When the test says they calculate the median.
Range.
Well, the range is a measure of dispersion. So if you're trying to answer on average, how far away is an observation from the mean? You want to figure out how spread out your data is. You use the range. But we're talking about the central measures of central tendency. So what type of data would you generally use the median for? Or when do you hear the median reported? The
Median is like center of the.
Yeah, so median is by definition the middle number. So you list out your observations, you stick one arm out one way, and your nose is where the median is. But why would you report on the median instead of the mode or the mean?
To find out upper low limits of the.
Okay, again, when you're talking about the limits, that's based on your variation. And when we get into our control charts, hopefully, that's been a slide that's been on stack, a slide that's been on deck for next week. We'll get there eventually. But this stuff is important. So if you don't have this foundation, it's hard to move forward. That's why I'm sort of slowing it down to make sure that you know what we're talking about. Because when we get into control charts, we'll talk about the control charts for the mean. You need to know why are we using the mean. Then we'll get into control charts for the dispersion. So we'll talk about the R chart. So you need to have a pretty good working understanding what the range is. And then we'll talk about the S chart, which is the control chart for the standard deviation. So you need to have a pretty working understanding of what the standard deviation is. So when looking at the chart, it's like, oh, that's what that means. Okay, so going back here, when would you use the median? Okay.
Like
Skewed.
skewed. Yeah.
Yeah, well, the data is skewed.
Or outliers.
Yes. Okay. So right, I'm going to New Orleans for a baseball arbitration negotiation. You go to law school too. You can have the privilege of spending $500 to go represent your school. You think you make the team? It's like, yay! They're going to fly me to New Orleans. No, you're on your own. Okay, at least provide me a hotel. No, you're on your own. We will provide you with dinner. Thank you. Very expensive dinner. Exactly. But full disclosure, the reason I'm really going is I don't have the New Orleans mug from this current series. So I'm spending $500 to get a little piece of ceramic so I can put it on a bookshelf. This would be with the other 220 odd of their friends. Yes. And I'll take a picture of it with my little llama, and everyone will be happy, including the little llama. Okay, but in baseball salaries, and most salaries in general, it's a heavily skewed distribution. So in baseball, it turns out there's a league minimum of about 400 grand, and there's players that make about 30 million a year. And the distribution looks kind of like so. Why do I make these X's instead of dots? No. Like so, and if you draw the profile, it looks like that. Okay, does that look like a normal distribution? That bell-shaped thing. Okay, why doesn't it look like a normal distribution? Well, it's truncated, right? No one earns less than the league minimum. So the normal distribution is symmetric. It's clearly is. Okay, so it's not normal. So then, is this left skewed or right skewed? It's clearly not symmetric. Right skewed, right? Because the tail wags the curve. It's like box shoes. Okay. Hey, someone actually laughed at that for once. Okay. So, if we reported out on the mean, right? The mean, we would get a number somewhere out here, right? Because Carlsen is way over there. So does that give us a good prediction of what the average baseball player makes?
No.
No.
So if we reported on the mode, so our peak of our curve, that would be our mode would be over here, right? Does that give us the best prediction of what the average baseball player makes? A good one, but it's sort of forgetting about that there is this whole clump of data over here. There's no data over here. So it's going to give us a understanding, but it's going to be somewhat misleading, right? Because we're ignoring a lot of data. So our means here. So what would be a better predictor of what the average baseball player makes?
Median.
Median, right? So 1, 2. So median.
39.
Thank you. Is that actually pretty good? Cool. Where's 20?
Yeah. No.
Here?
Yeah, it's like this.
This guy?
Yeah, looks like the second.
Cool. But we just want the column that he's in. So our median's here. So our mode and our median are pretty close, but we saw that when we just kind of eyeball it, that we'd expect that our best predictor is going to be somewhere in the fat part of the curve, right? And so our median here, because we have highly skewed data, gives us a better depiction. And if you remember the Warren Buffett walking into the bar example that I talked about, right? Everyone remember that?
Mhm.
Yeah.
And the fact that when Warren walks into the bar, it then raises the average salary of the guy sitting in the bar to a big number, a couple $1 million a year. But if you're trying to pick up someone that's making a lot of money, and it would be accurate to say the average guy in that bar is making $1 million, but if you grab one of the other 6 that isn't Warren Buffett, well, he's making 60 grand. So if you're, I got in trouble in the class saying this recently. I'm trying to walk back. Okay, so we use the median when we have skewed data because as we came up with and we talked about is that the median is more tolerant and less responsive to outliers and skewed data. It still gives you a good understanding of what's going on. Everyone cool with that? Cool. Kind of cool out. Okay. So what we started to do last class, well, in the slides that we're going over, is we also talked about the different types of distributions, right? So we talked about probability distributions. And way back when, if you rattle your brain around enough, we talked about the central limit theorem, right? So what the central limit theorem says that regardless of what the shape of the underlying distribution is, if I take a sample from it and I average those samples, and I take a lot of those averages will follow the normal distribution. Kind of doesn't make sense, right? So I start out with a uniform distribution of dice. Right. And the probability of rolling any given roll of dice is 1/6, right? Because the sum of all probabilities has to add up to 1, right? So if I roll a dice 10 times and I record the average, I hopefully will get something in the middle, right? So something like 3.5, right? So I roll the dice 10 times. So it's actually a set of rolls. 4, 1, 2, 2, 4, 5, 1, 2, 7, 8, 5, right, 2, 7, 8, 9, 10. So we come up with that set of rolls, right? 6, 11, 13, 15, 19, 24, 25, 27, right? Yeah, agree? And we divide that by 10, we get our average is 2.7, right? Okay, so we start with 1, we come up over here, so theoretically you could have an average of 6, right? Is it possible to have an average roll of 10 dice where the average roll is 7?
No.
Could this average have worked out to being 7? Could this average have worked out to being 0? Could
No.
it get 0? Is 0 up? Right. Probability of rolling, having the average of 10 rolls of a dice being 0 is 0. Just like the probability of rolling a dice 10 times and the average being 8 is 0, right? You have to get an average that's somewhere between 1 and 6. Everyone cool with that? None?
The dice is from 1 to 6.
Yeah, standard dice.
So you couldn't possibly roll 0.
You're going to get a number between 1 and 6. You roll the dice. You can't get a 0 and you can't get a 7. So can the average of numbers between 1 and 6 be 7?
No.
No, you have to get a number that's somewhere between 1 and 6. Cool. So our average, so this is the probability of a given roll, right? This is our count.
0 at the end. Yeah, I thought it was a 0.
You get a 0.
See, I thought he had 0 at the end. See on your board? No,
Oh, I'm sorry.
that's why I said. Okay.
All
right.
Bad penmanship.
Okay.
Bad penmanship. Okay, so this is the averages. Okay, so we just did this once. We got 2.7, so somewhere over here. And what the central limit theorem says that if we keep repeating this, we will ultimately get the normal distribution back. If we just take our 10 rolls, we do it again, we plot the 2.7, we do it again, we get 3.3, we plot that. Rinse, lather, repeat ad nauseum. We'll eventually get back out the normal distribution. It's kind of weird. We start out with the probability of any given number being flat, like that, right? And then we end up with something that looks like that. Does that make sense to anyone? It shouldn't make any sense. And there's no damn good reason why, other than it does. It's kind of cool. It's one of those sort of magical properties that's kind of neat. And that's something that we'll be exploiting as we move through the class. When we get to our control charts, it makes it less important that we know the distribution of our variation in our part length or our part weight. But if we take those averages, we know what distribution it follows. So if we know what distribution our data follows, we can make predictions. And then we can use that in our control charts to differentiate what values are likely to be seen from those that are unlikely to be seen. Yeah. So it's a good bet. So the central limit theorem allows us to take non-normal data, which we would use the median to describe. And if we take samples, average those samples, and then look at the sample averages, the sample averages will follow the normal distribution. You can expect there to be 2 to 3 questions on the exam related to the central limit theorem, and it's really confusing. And the only way for you to get familiar with it is just to think about intuitively what you're doing, and more importantly, why you want to do it. We have a lot of tools that allow us to deal with normally distributed data. So we want to get our data to be normally distributed. But lots of things in life don't follow normal distribution. So last class we flipped coins, right? Some of you were here, some of you weren't. And does a coin flip follow normal distribution? What do you think? Raise your hand if you think flipping coins, you flip a coin, right? Every football sporting event starts with flipping a coin, right? Does the probability of flipping heads versus the probability of tails follow normal distribution? What do you think? You think it does?
Yes.
Okay, raise your hand if you think it does. Raise your hand if you think it doesn't. Gotta vote. 10 ladies in the middle. Everyone's wrong. Okay, cool. Okay, so we have heads, tails is example of what type of data? Nominal, ordinal, ratio, or interval?
Ratio.
Well, it's ratio.
Okay, ratio means it's rational zero, right? So if I'm categorizing things into heads and tails, and I'm counting up the number of heads and the number of tails, does it make sense to, is there an interval between heads and tails? No, so it's not ratio and it's not interval. Because if I write heads, very good. It's nominal because, well, they have word meaning, categorical meaning, but I can't take the average of heads and tails and make heads or tails of it. Remember the deal. You don't have to laugh at the jokes. You have to give me some sort of an evil look. Okay. And it's all recorded so you can watch these jokes again at home and share them with your friends. At some point, someone's going to send this into like Comedy Central of like what not to do when teaching a class, and I will have my 2 minutes of fame for something stupid. But going back to that. Okay. So heads and tails are examples of nominal, right?
No numerical sense.
Okay, so what's the probability, what percent of the time on a fair coin will I flip a head? 50%. And what's the probability that I flip a tail?
50%.
What's the probability on one coin flip that I flip a head and a tail?
You can't.
0. Okay. So the probability, it's kind of written kind of hokey, of flipping a head. So the probability of what's in the parentheses equals 50%. The probability of flipping a tail is 50%. It's almost Super Bowl season, and people bet do the proposition bet for who's going to win the coin flip. How many of you have actually done that prop bet? Not even like gone to a Super Bowl party and for people that aren't football fans so they can play along? Anyone heard of people betting on the coin flip? Okay. That's killing me. Okay, so the probability of heads and tails equals 0%. So the probability of heads, what's the probability of flip a head or a tail?
100.
Yeah. So,
50%, right?
Only here.
It's like 50-50 that you're going to flip it, right?
well, you flip the coin, right? So what's the probability that you get a head or a tail?
50%.
No, that's if you get a head.
50%.
You get it's 50% that you get a head,
Right,
and it's also 50% that you get a tail.
right.
So what's the probability that you get a head or a tail when you flip the coin?
100.
100%, right?
Okay.
Okay, so this will be, the thing that looks like an N is end. The thing that looks like a U is or. I might have said it backwards, and I still caught myself doing it. That's why I said we're going to come back to it because I said it backwards last class. And I was hoping we would forget I said it backwards. You guys remember? It's kind of funny when you teach a class, and this happens. And I've had it happen to me as a student and as a professor. You occasionally will misspeak, and your students invariably remember when you misspeak, and they for some reason don't remember the stuff like when you say it correctly. It's like, wait, I said it correctly 7 times, and the 8th time I said it backwards. It's in the slides correctly. It's labeled correctly in the slides. I just misspoke when I said it last class, and I caught myself when it was coming out of my mouth, and I apologize. The way I remember it, what I remember it, is that the U is like a bucket, and it holds more. Okay, but okay, so we did this. So what's the probability that I flip it and it lands on its edge, like that Twilight Zone episode? Have anyone seen that Twilight Zone episode?
Yeah.
You've never seen the Twilight Zone? Okay, let's start with even more basic. How many of you have seen the original Twilight Zone at one point or another? Yes, you are. You are absolutely missing out. I tried to watch it in high school English class, middle school English class, and we were doing a unit on short stories. But there's a very famous episode where a gentleman flips a coin and it lands on its edge. And he then has this impeccable luck until the coin falls, and that's the product. So it is physically possible to flip a coin and get it to land on its edge, it's just really small. So technically, the probability of getting a heads is a little bit less than 50. And the probability of getting a tail is a little bit less than 50. Because you have this minuscule but not 0% chance that you will get edge. Can you imagine what would happen if on the Super Bowl they flip the coin and it gets like stuck in the turf? Such that it's. And if you're a football fan of a particular vintage, you remember that infamous coin flip where they called it heads and tails. And now that they had to change the procedure, so you have to call it before it's in the air, you have to call it when it was in the air. Everyone remember that? It was the Steelers, right?
Yeah.
Okay, so now let's make it a little bit more complicated. So you flip a coin twice. All right, what are the outcomes if you flip a coin twice? You can get 2 heads, right?
Mm-hmm.
Heads and the tails.
Mm-hmm.
Tails and a head. And 2 tails. Right?
Mm-hmm. Yep.
So what's the probability that you flip 2 heads in a row? Anyone have a coin? You gonna make me do this?
Oh.
Or do you want to think about it? So what's the probability that you flip 2 heads in a row? 25, right? We have 4 outcomes. They're both equally likely, right? Okay, so 25% that you flip 2 heads in a row, right? Everyone see why that is? Probability of flipping a head and a tail?
20.
25. Tail and a head?
20. 20.
Okay. So what's the probability of flipping a head?
Uh, 75.
Yeah, 75%, right? What's the probability of flipping a T and an H? That's a different question.
Oh, T and H. 25. Yeah, I think 50.
50, right?
Yeah,
So this guy's got a tail and a head, this guy's got a tail and a head.
Yeah, 50.
Yeah, because I didn't say that order mattered. I just said that you flip a tail and a head.
Right.
Cool. What's the probability that, given that, I flip tail, 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 on 2 flips that I get 3 tails?
75.
No, I get the sequence tail, tail, tail.
No, it's so for that. It's got to be less than 75, right?
No,
I flip the
100%.
coin twice and I get 3 results. Oh, zeros. Right? So you can only predict results that are in your solution space. Kind of an important concept. And it's really, they'll ask you a silly question on the exam like that, and you'll get tripped up by it. So they'll think that you're asking like, what's the probability of getting 3 tails? And they'll give you a distribution for 2 coin flips. And it's like, that's not possible. And 0 will be an answer. It's like, oh, damn you. Also, one of the things we'll talk about when we get more into our measurement section is to do a common sense check when you look at your data. So if you are only doing 2 observations and you get 3 results, that generally means there's a problem. A lot of times if you're doing data analysis, you'll find that and you have a long data set, you'll find that something is reported to 3 decimal points, and then magically it only gets reported to 1 decimal point. And what happened to those 2 decimal points? Or you'll find that you have one number that's really much bigger than the others, where someone might forget to hit the decimal point. Anyone in the quality world seen that? Something like that? Okay, some people are nodding their head. Anyone been guilty of that in the technician side and mistype the number?
Yeah.
Okay. Anyone think that's non-value added? Remembering value add is anything that changes the fit, the form, and function of a good or a service that your customer is willing to pay for. Is keying in data value added? And is correcting the screwed up data value added? Cool. Okay, so big important concepts in probability for this exam is that the area under this curve has to add up to 1. 1, right? 1 or 100%. And just remember back to your basic middle school math is that you can represent numbers as whole numbers, or you can represent a decimal as a percentage and percentage as a decimal. Sometimes people get kind of wound up on that. So remember this 50%, you very easily could write it as 0.5. Same number, just different representation. Cool. So the area under the curve is 50%. The height of the curve defines how likely it is to observe that value. So I am going to observe a head 50% of the time. I'm going to observe a tail 50% of the time. Good. Okay. So now let's go drill into this a little bit deeper. And just if you're following along, we're into the last couple of slides on there. We're going through the probability rules. I wrote down the rules. I don't think they make much sense for you to just read on them. So again, going with the theory of the course is that you get it presented by me battling. Now you get the video of me battling. You get it through the slides, and then you also get it through the book. So you'll get there. It's the slide before that. And at some point, I'll get around to the number in the slides. Yeah, we're talking about conditional probabilities now. Okay, so what's the probability that I flip a head and a tail? A head and then a tail, in that sequence. I flip the coin first, get a head. And then I flip the coin again, get a tail.
50.
Well, the order matters this time, so I get head. So I flip the coin 1, probability of flipping a head is 50%, right?
Mm-hmm.
Probability of flipping a head tail is head tail, order matters. Right. 25%. So why is it 25%? Besides that, you intuitively think it's 25%, and I threw it up there as 25%. What do you think? Any ideas on why it's 25%?
Because there's 3 other possibilities that could happen.
Okay, but those don't all have to be the same likelihood, because as we saw, if we make it such that order doesn't matter, so if we drew it such that the probability of getting 2 heads, the probability of getting 1 tail and 1 head, and the probability of getting 2 tails, we get something that isn't. Right? Right, so we get something that they're not equally likely if we're just looking at the number of coins. Okay. So why, if the probability of getting 1 head is 50%, what's the probability of getting 2 heads? So it's 25%, right? So why is the probability of getting a head and then another head 50%?
Why is the probability of getting a hit and another hit 50%?
Yep. Exactly. So I flipped.
You just said
I flipped the first coin, right?
2 heads is 25, right?
So I flipped the first coin. What's the probability of getting a head?
50%.
So we flipped the first coin. Coin one. So we have 50% chance of a head. Then we flip coin two. What's our percentage of getting a head? 50%.
Oh, you're talking about on the second flip.
Yeah, talking
Okay.
about the second flip.
Okay,
First flip, chance of getting a head, 50%.
Right.
Second flip, chance of getting a head.
50%.
Okay, that means that they're independent, right? The first observation has no impact on the second observation. Okay, so when you have independent observations, the probability of two events is simply multiplied. So we take the probability of event one, so the probability of getting ahead, multiplied by the probability of event two, ahead. So 50% times 50% is half of 50. 25. Now let's make it really hard. Probability of getting 3 heads in a row. So if I flip a coin a third time, is the probability of getting a head still 50%? Is it affected by the prior flips? So what's the probability of flipping 3 heads?
70.
So probability of 1 head is 50. Probability of 2 heads, 25. Probability of 3 heads, 12 and a half. 1/8. You know where I'm going with this. Okay, now let's make it really kind of make you think. The probability of flipping 3 heads in a row and then a 10.
Okay, so 12.5 times 50%.
Yep.